Manipulating Data Part 2 of 2. In this nugget, we complete our basic grand tour of the fundamental data manipulation language, DML statements, in Oracle SQL. To that end, we're going to look at how to delete rows from a table using delete, paying special attention to what's called referential integrity. We always want to remember that as a relational database system, Oracle uses referential integrity rules to determine what happens when we delete data across related tables. We're also going to spend time in this nugget understanding the TCL, or Transaction Control Language statements, in SQL. In my opinion, nobody should call himself or herself proficient with SQL unless and until they understand all of the mechanics and practical aspects of transactions in an RDBMS. Let's get to work. As previously discussed, the delete statement is our fourth DML statement, the other being select, insert, and update that we're covering in this course. And delete is sometimes confused by newcomers with the truncate statement. You'll recall that truncate will clear out all of the rows of a table. It will leave the table structure intact, that is to say the table object, its column names, its data types, its constraints, but truncate clears the decks, as it were, as far as performing a mass delete of the entire table. Now, delete is much more granular. Yes, we can use the delete statement to remove all rows from a table, but the great beauty of delete, as opposed to truncate, is that we can use the where clause to do filtering to determine which rows we want to remove. Now, the idea of deleting any data in a relational database management system ought to be enough for us as DBAs to get a little bit leery, a little bit queasy perhaps. As I've mentioned so many times, businesses, that is to say most businesses operating in the 21st century now, store their entire business life in a database system. And the idea of deleting permanently any data from that, especially when we have, again as previously discussed, federal mandates here in the States like SOX, Sarbanes-Oxley as it's called, HIPAA in the medical field, and there are others that mandate by law that you keep data for X amount of days, weeks, months, years, or forever for compliance purposes. You may also have service level agreements with your customers such that you guarantee you'll retain their data for X number of years. So to that end, many companies never permanently delete data from a database. Yes, we'll use the delete statement to remove rows from a source table, but we can also make use of another database object called the trigger that's beyond the scope of this training. But as I've told you in the past, just in passing, trigger is SQL code that can execute automatically before, during, or after any other statement is created. So I know what some businesses do is they will have a trigger waiting on each table looking for the invocation of the delete statement, and it will allow the delete statement to happen on the source table, but not before those rows that were deleted are copied out to an archive table, you see? So there you have the best of both worlds. You're able to remove rows from a table per your business needs, but you're also able to restore those if you need to and keep those rows safe in an archival table. Now then, let's get to the specific syntax, shall we? It's pretty straightforward actually. If we want to delete all rows from a table, similar to how truncate works, we can issue delete from and then the table name. More commonly, as I said earlier though, you'll want to perform row level filtering. To do that, we keep the delete from line, but we just specify a where clause. And again, the where clause can be anything you want. It can be a straight static assignment like you see here, prod ID equals 5,000, or it can be an expression if you want to delete more than one row, where prod ID is between 5,000 and 10,000, where date introduced is greater than January 1st, 2001, etc. All that kind of expression work that we've done to date applies here. Now, where things get a little bit more complex are the ramifications of the delete statement when you have related tables. This brings up referential integrity, or RI. Now, referential at base, the word is reference. So obviously we have related tables. We have a primary key field in the one table related to another column, a matching column in another table to which we've applied the foreign key constraint. References, in fact, references is one of the keywords, as you know, that we use when we apply a foreign key constraint to a column in a table. The reference on the foreign key side means whenever we're adding new data to this related table, we have to make sure, or actually Oracle will make sure for us, that any data we put in that foreign key column exists in the source table. We're maintaining integrity. Integrity means we don't have the problem of, for instance, data that does not exist in the source table that exists on the other table. Let me make this a little bit more concrete. Perhaps the table relationship is between an employees table and a sales table. It would make sense, I hope, that when we're adding new rows, that is to say putting in sales, we're not going to ever refer to an employee, let's say a salesperson, who doesn't exist in the employees table. That would obviously violate integrity and cause all sorts of havoc. You might even lose your job for an error like that. The good news is that referential integrity rules in Oracle and any relational database system worth its salt will actually prevent that from happening, and we saw that in the previous nugget. Moreover, just to get a little bit deeper on the foreign key constraint, when we set a foreign key constraint, I haven't showed you this yet. I'm going to introduce this particular wrinkle in the demo for this nugget. You can customize what happens in an update or a delete scenario. Do you want to just restrict that cascade from happening? Do you want to allow it to happen? Or do you want to set null? Now again, what does that mean? Let's imagine we have an employees table and a sales table once again. You have the relationship set up, primary key to foreign key, let's say with the EmpID column. And for our foreign key option, we choose restrict. What this means is, let's say employee ID 100 leaves the company. You might think, okay, I'm going to delete that row from the employees table. If you have foreign key restrict, then that delete will fail, and Oracle will tell you that you have instances of employee ID 100 in a related table, and it just isn't going to let it go through. If your business needs dictate that you do want that to go through, which to me is a very, very tricky option indeed, you can set cascade on either update or delete. Now the problem with cascade delete, friends, is that it deletes entire rows. That is, when we delete employee ID 100 from the employees table, that's going to cascade and delete every row from the sales table that references that employee. As far as Oracle is concerned, it's maintaining referential integrity because we won't have any orphan references to employee ID 100 in our sales table. But I think you can immediately see the problem. Sales managers are going to work in their numbers and find data missing, and that's obviously what's happened here. Cascade, in my experience, works better with updates. I find that cascade is less destructive in an update situation as opposed to delete. Third option, which is kind of in the middle in terms of restrict, which is very conservative, and cascade that's very liberal, is we have set null. And what that would do is, again, to come back to our example, we delete employee ID 100 from the employees table. That does succeed. And then for every sale in the sales table that references EmpID 100, we're going to see a null value. Now, obviously, if we have that column set to not null, that's going to be a little bit of a problem, but it's at least a stopgap mechanism. You can then procedurally or manually edit those null values and maybe reassign them to a new employee. It depends on what your business needs are. The bottom line is Oracle gives us plenty of customization options on how we're going to handle deletes in a relational manner. In this first demonstration, we're going to work with the delete statement, and in particular, how that relates to the foreign key constraint. We're logged in, as usual, to our Oracle database through SQL Developer. I'm logged in as the HR user, and to set the stage for our work, I'm going to run create table a couple of times. I'm going to create a sample table called T10 and another called T11. T10, actually both of these are very simple tables. We have an ID column that is going to serve as our primary key. You see I've used the constraint keyword to name my primary key constraint, T10PK, and it's keying on that column. The second column in T10 is called data, and it's just not null, no big deal. Table 11 is going to be a related table, and I can prove that by showing beyond the ID and data columns, we also have a rel ID column that uses the same data type as ID in table 10, and I've created a foreign key constraint called T11_FK, whose local reference is rel ID right here, and it references in the remote table T10 the ID column. So this is pretty plain vanilla stuff. We've already covered this material in a previous nugget. Now that I've created these objects in SQL, let's come over to our connections window in SQL Developer. I'll right-click table T11 and let's investigate a little bit greater detail of how the foreign key is set up. We'll right-click and select Edit. We've seen this before, the Edit Table dialog. dialog makes table maintenance a pretty simple procedure actually. We'll select foreign keys. This is our foreign key that we created, and I want to draw your attention down to the bottom here. On delete, the default action is restrict, but we can make another choice here. We can have it cascade or set null, and we can set those cascade options in SQL. Of course, we don't have to do it graphically. The reason I am doing it graphically is to demonstrate that everything we do at the command line is transferable to SQL Developer and vice versa. So right now we can rest assured that our cascade delete is set to restrict, so it's not going to allow any cascades. Let's enter some data, some sample data into those tables. I'm going to insert 3 rows into table 10, values 1, 2, 3, blah, foo, and bar. We'll now do the same thing on table 11. I'll insert 3 rows. Remember, the third row is the rel ID column, so hopefully it makes sense that we're going to need to insert in this third position only values that exist in table 10. No problem there. Just to demonstrate that, I'm going to modify this final insert statement. I'm going to call this value 133. I'm going to call the data column invalid, and I'm going to reference or try to reference an ID value from table 10 that doesn't exist. Let's just verify that referential integrity is working, and sure enough it is. We get an ORA error, tells us that the foreign key constraint's violated. A foreign key value has no matching primary key value. No big deal. Now let's proceed here with the delete statement. The first statement I'm issuing here is delete from table 10 where ID equals 001. Now at first blush you might think, okay, well that's cool, right? I mean, we should allow that to happen. But remember that we have instances of 001 in table 11. Let me quickly demonstrate that by running a select splat from table 11. And we can see, sure enough, 001 or rel ID value 001 shows up in not 1 but 2 out of the 3 rows. So we kind of know what to expect before we do this, but let's try it anyway. We'll select this delete statement, send it into Oracle, and sure enough, we get another ORA error. Integrity constraint violated. In this case, we attempted to delete a parent key value that had a foreign dependency. Delete dependencies first, then parent or disable constraint. That's some not all that intelligible instructions, quite honestly. Of course, we can get investigative data on row ID 1 by running a select from T10 where ID equals 001. If we do need this delete to go through, remember we have to modify the foreign key constraint. So let's again investigate table 11, and in its foreign key properties, let's change the delete value to cascade, just for grins, to see what happens. So if we now come back, let's see if we can delete row ID 1 from table 10. It says 1 row deleted. Well, where is that going to put us in table 11? See, it's going to give us removal of those related rows. That's not all that good. I've issued the rollback command, and now let's select star from T11 again, and our data comes back. Now I'm letting the cat out of the bag a little bit. We're going to be working with transactions in an upcoming demo, but because I haven't explicitly committed our work thus far, it's all just in memory. We haven't committed anything to disk. You note in SQL Developer, you have commit and rollback right up here on the toolbar. The buttons are next to each other, or it's just as easy for our purpose in studying for the SQL exam to issue it from the command line. So in effect, I've undone my change. Now let's try to delete data from table 11. In this case, we'll say delete from table 11 where data equals banana. And we can see here in our query result from earlier that this should remove the third row in that table. 1 row deleted, no problem. So if we now attempt to select that row from table 11, it doesn't give us anything back because banana is in fact gone. Now let's turn our attention to the transaction, which really is the basic building block of any relational database system. A transaction, sometimes you see the word transaction shortened to TX or TRX, is an atomic unit of work. Now, atomic is referenced on this whiteboard. You'll often see when we discuss transactions, transaction-oriented databases, of which most databases, especially relational databases, do subscribe to the transactional model. model, we hear talk of what are called the ACID properties, or sometimes this is referred to as the ACID test to determine whether or not a database supports transaction processing. And let's go through these. As I said, a transaction is a single unit of work that either succeeds 100% or fails 100%. That's actually the A in the ACID properties list. Atomic means indivisible, right? So at the transaction level, we can't break it up any more than what's there. It's the fundamental, most basic element of data to be put into a database. And that doesn't just refer to inserts, but it also refers to updates, deletes, creates, alters, drops, anything you do in a relational database. And that atomic unit of work needs to succeed 100% or fail 100%. We cannot have inconsistent data, which takes us to the second hallmark of a relational database system. The C stands for consistent, that we have no intermediary or partial data. I'm going to give you the classic example that we use when we teach relational theory, the banking, account debit and credit example. I stands for isolated, and this means that transactions in a database need to be scoped to their level of commission. Now, what do I mean? That definition is probably more complex than the term itself. Basically, it's like this. If I'm in a table and I'm using the update statement to modify some rows, and we have another user coming along who wants to run select statements against that table that incorporate those rows, we want to make sure that the users who are coming in see consistent data, that they don't see changes every time they run a select statement. While I'm modifying, updating those rows, it's not going to be until I commit those changes or make them permanent that any other user will be able to see those changes. Now, once I commit, yes, the same user might run select a second time and see data that's changed, but that's data that's been committed and is considered to be durable. That brings us to the final initial in the ACID acronym. And that means that when we commit a change in a database, that transaction data needs to be permanent. That is to say, it needs to survive across Oracle server restarts. It's not subject to memory loss. Any data that's stored in RAM, obviously, is going to go away if a power surge or power sag interrupts the machine and causes it to shut down or reboot. The classic example in teaching the transaction as an atomic unit of work is what you're seeing on your whiteboard. This comes to us from the Oracle documentation, but it's a standard example. And what we've got going on here is an individual who wants to transfer $500 from his or her savings account at their bank into their checking account. And when you look at this, it's actually broken out in this example into not 2, but 3 discrete steps. We have an update statement where we're updating the person's savings account and setting their balance field to its current value minus 500. So we're decrementing their balance in their savings account, and we're filtering only for their account ID, obviously. Now, in a transfer situation, we remove money from one account, but then we have to add that data, or add that money, I say, in this case, to another account. So this invokes a second update statement where we're updating the checking account, setting the balance to its current value plus 500, again, where account equals whatever the individual's account number is. The account number is different here, I think, to give us the idea that with banks, at least with my banks, my savings account number is different from my checking account number. Now, this particular example has a third step where we're journaling that transaction. In other words, we're making a record of what just happened. So we're inserting into a journal table the next value. It must be we have a sequence here to maintain a primary key value in the journal table. You remember how we used the next val method to invoke the next integer in a sequence. 1b, whatever that is, 3209, 3208, 500. So these are data fields that reference various accounts and then the amount that's shifted between those accounts. Now, let's ignore the commit work statement for just a second. Which of these, or all of these, or some of these represent a transaction? What do you think? Well, the answer to that question is it can be any of the above. That is to say, in Oracle, you can issue a commit statement to tell or instruct Oracle to make the change permanent at any time. That is, we can run this savings account update and then issue commit or commit work, and then issue the second update and commit that, and then finally do our journal insert and then commit that. I'm sure plenty of businesses do it that way. I hope you're seeing a potentially huge problem with that approach, though. If we have transactions defined at the statement level, what happens if we have a failure? That is, what if our first commit happens just fine, but then we have a problem here during this increment checking account step, and we have to roll back? Well, as we're going to learn in just a minute, the rollback statement will roll back or undo any uncommitted work, but it will keep committed work. Obviously, in the acid test, durable means committed work stays forever unless we explicitly delete it and commit that change, you see? So what I'm trying to get across here is that you as a database administrator / database developer, you need to think in terms of how many statements comprise that unit of work. You as a DBA and database developer actually can determine whether your transactions are single statements or multiple statements. So to review, transaction control language or TCL statements, the commit statement makes any changes permanent in the database. Now you might be thinking, at least I hope you are, well, do I have to issue a commit every time I want to make a change permanent? The answer to that is no. Oracle 11g will auto commit under certain, actually two main situations. One, when you issue DDL, create, alter, drop, etc., and DCL, grant, revoke, and so forth. Those are auto committed. You do not have to issue a commit. Those, I think, are considered to be important enough statements such that Oracle will go ahead and commit those line by line. That is, you can issue 3 create table statements in a row, and each one of those will be individually committed. The other case where an implicit or auto commit occurs is in your client software. Now this is going to depend upon who makes your client software. As I mentioned earlier, the first-party software that Oracle gives us, namely the SQL Developer GUI tool and the SQL Plus command line client, will do an auto commit as long as you gracefully disconnect or exit your session. Disconnect and exit are both SQL Plus statements that, in the case of disconnect, will gracefully, well, end your session but keep you in the tool. In SQL Plus, in the command line tool, exit will end your session and actually take you out of SQL Plus altogether. Both of these commands, though, will ensure that any work that hasn't yet been committed is committed. You want to be careful using Windows controls. The old X button in the upper right depends on the software. SQL Developer is smart enough to recognize that and ask if you want to commit your work, but many other tools will not. So you'll wind up with your work just getting implicitly rolled back. So be careful. We mentioned this term rollback several times. This simply means that we're undoing uncommitted work. We obviously have to issue rollback if we want to do so voluntarily before a commit. Once you commit the data, it's there forever, unless, as I said, you make another change and recommit on that second change. You'll find that Oracle will perform an automatic rollback if, for instance, an error occurs. Again, the idea here is that Oracle wants to keep data as consistent as possible, and consistent means committed. I mentioned in the previous whiteboard when we looked at the account debit and credit example that it's up to you as a database developer to batch transactions together that make the most sense. In the account debit and credit, we had our debit, credit, and a journal step. We obviously want to batch all of those together, and basically all that means is you issue all of your commands and then issue a commit at the end. You can use PLSQL to provide error handling and additional features that are beyond the scope of what we need for the SQL fundamentals test. You can also use the set transaction name command to name transactions. Some businesses are really big on documenting every change that's made in a database, so you may, if you find yourself in this situation, naming your transactions so that you, your colleagues, your boss, your customers, your clients, whoever, understands what you're trying to do in defining those units of work. The final point is the save point, and this gives us, again, granular control, in this case not over what defines a transaction, but granular control in rollback. Now, if you had this 3-step example batched as a single transaction, debit, credit, and journal, what's going to happen if during the journal step an error is raised? Well, as I mentioned, Oracle will auto roll back in the case of an error, and the question is, how far will it roll back? You see, in this case it's going to roll all the way back from before you issued that first debit statement. Now, in longer transactions that have many steps, that may be an inefficient way to work. So you can create save points in a transaction batch such that you can selectively roll back to a particular save point. It will keep some of your work active and then undo the rest. So it's just all in the name of giving us as data designers as much flexibility as possible. In this second demonstration, we'll work with transaction control in Oracle Database 11g. We left off in the previous nugget by working with the delete statement and looking at the implications of the foreign key constraint cascade options, and we also touched a little bit on the use of rollback to preserve the previous state of data. I'm going to start by running truncate table against T10 just to clear everything out, and you'll notice, sure enough, we get an error that tells us we have related records in one or more other tables, you see? So as you start adding constraints, you're going to find that your flexibility, being able to hither and yon run truncates and deletes and drops, is going to get blocked by Oracle in the name of maintaining that data integrity. And that's, again, fully expected. We expect that to happen. Okay, so what you're seeing beginning on line 57 are a couple inserts. We're going to insert some new data into the table. I'm going to change the values here to make them unique. Before I run these two statements, let me just run a select star from T10 to see what's in there now. I have 5 rows of data that have been fully committed and therefore should be visible to any user that has permissions. Now HR, this user, owns this table T10, so we need to grant permissions if we want, say, the Scott user to be able to select against it. So I'll run grant select on T10 to Scott to give him permission, which I just did. And now we'll switch over to Scott session, and he should be able to run select star from HR.T10. HR dot is the schema prefix. We need to do this to facilitate name resolution, unless, as you know, we could create a synonym per our previous discussion. And sure enough, Scott sees the committed data in that table. Now, what if we add more data, like you see here? If I add this row here and then run a select from HR, obviously I'm going to see that new row, 111. I haven't committed that change though. So if we come over to Scott's session, we don't see it. You see what I mean? Here we're dealing with the ACID properties of transactions once again. Transactions should only be visible to other users once they've been committed in the database. So if I explicitly run a commit statement, which I can do a couple different ways, either from SQL or using the toolbar, I now can come back as Scott, rerun that query, and now I see the 6th row, you see? So again, that's touching on the ACID properties of transactions. Now I've already committed, so rolling back isn't going to do any good. Let me try to insert yet more data. I'll call this row 222, and we'll change the value to MNOP. 1 row inserted, run a select from my local session, there's the row, come over to another user, run the query. We do not see that data yet, and we can keep on trucking and keep on issuing DML statements all day long, but it isn't until we issue commit that the changes will be made permanent in the data files, and other users who have access to those resources will see the changes. By contrast, if we change our mind and want to undo our transaction, we can issue rollback, tells us rollback is complete. So now if we select against the table from our local session, we do not have the MNOP row, and of course just academically we'll come back to Scott and verify that it's not visible to him either. Final thing I'd like to show you is the save point. We have, beginning on 88 here, a series of insert statements. Interspersed are save point statements. When we use the save point command, we issue the save point keyword, space, and then the name of the save point. And as previously discussed, this will allow us to selectively roll back. So as you're working through a large transaction batch, before committing any of it, you decide, okay, I want to undo some of my work, but not all of it. So to kick this off, let's select the entire batch in which we're going to create a few save points here. Tells us in our script output that we've inserted those rows and we've created those appropriate save points. Now, how do you use save points? First, before we do that, let me just run select star from T1 to make sure that although it's uncommitted at this point, we have those rows added before SO1, before SO2, before SO3. Let me just throw in an order by here. There we go. We can roll back selectively by supplying the keywords rollback to and then the name of the save point to which we are going to roll back. Tells us rollback is complete. Let's again run that select statement. So if we rolled back to the second save point, then we should still see what's before or ahead of that save point, which are the before S01 and before S02 rows. And sure enough, that's what appears. Let's commit our work and then run a final select to verify that we have what we want, and we do. Manipulating Data Part 2 of 2 review. At this point, you have a pretty good grasp of most of the basic SQL commands in Oracle 11g. We finished up DML in this nugget by examining delete. You understand not only how to use delete now, but you also should know a thing or two about referential integrity, a little more deep information on foreign keys, and how we can customize the foreign key constraint to deal with cascades in a delete situation. We also understand transaction control language statements, stuff like commit, rollback, save point. So now I'm confident that you not only understand how to manipulate data, but you also know how to manipulate transactions, which, as we know, form the atomic unit of work in any relational system. I hope that this has been informative for you, and I'd like to thank you for viewing.